Hello everyone, and welcome to this video on norms in an inner product space. Alright, so what I'm going to do in this video, I'm going to start off you know, with Euclidean space, R2, R3, spaces where vectors can be pictured, and go over the concept of the norm of a vector in those spaces, and you'll see how it's related to length or magnitude of a vector in R2 and R3. Then I'll talk about some properties of norms or lengths, magnitudes in R2 and R3, and go over some examples demonstrating those properties. Then I'll talk about unit vectors, and then we'll get into other norms besides the one we're familiar with, right? The one where you find the length. Talk about some other norms that exist on Euclidean space. So, and again, not just R2 and R3, but R4, R5, R6, whatever, R, and show you some examples of those, and then finally get to the title of the video here, the concept of a norm in just on a general inner product space, right? So on any vector space with a well-defined inner product. And you'll see it's analogous to the concept of length or magnitude in R2 and R3. Alright, so like I said, we're going to start off with a little bit of a recap. Right? I'm hoping you've seen the dot product before, I'm assuming that, and also how to find the length or magnitude of a vector in two-dimensional, three-dimensional Euclidean vector spaces, right? R2 and R3. So I'm hoping this is a bit of a recap for you. Lengths or magnitudes of vectors, which are also called the norms of a vector. Right? The length or the magnitude is also called the norm of a vector in R2. And I got in parentheses here and R3. The only examples I'm going to show are in R2 because they're much easier to draw on a coordinate plane and demonstrate in some examples. So suppose we're given the vector space R2 with the inner product on that vector space being just the dot product, right? The Euclidean inner product or the standard inner product, however you want to say that. I'll just say the dot product for the most part. And again, all this same stuff I wrote here would hold for R3, right? Just add one more component. So in R2, with the dot product as its inner product, when you think of R2 as an inner product space, the length or norm or magnitude, right? The length or norm of a vector, say vector v with two components, right? I'm sticking to R2 here, v1 and v2, was defined this way, right? Remember, you could set up a little, and I'll show you a picture later. When you represent a vector in R2, you draw a little arrow, and if it wasn't a horizontal or vertical vector, you could set it up so that that vector was the hypotenuse of some right triangle. And the length of the vector is just the length of that hypotenuse, right, which I'm getting from here. Now the symbol for norm of a vector are like these two little double absolute value symbols, right? They're not called double absolute value, so please don't say that. This is the norm of v, or the length of v, the magnitude of v, equals the square root of the sum of the squares of the components, right? v1 squared plus v2 squared. And again, the same thing would apply to R3. If you had a vector with v1, v2, and v3, the norm of the vector would be the square root of v1 squared plus v2 squared plus v3 squared. Right? It's just the general norm in Euclidean space is the square root of the sum of the squares of the components. Right? But right now I've just got R2 up here. Well, the sum of the squares of the components, that's just the dot, if I'm using this inner product on R2, that's just the dot product of the vector with itself. So another way of expressing this norm of v is the square root of the dot product of v with v. Right, and this is this dot product. Remember, I said the dot product. It is an inner product on R2, right? It's an inner product on any Euclidean space, R2, R3, but just specifically R2 right now. And so yet another way this could be expressed, which is going to be very important for us later in the video, is that the norm of a vector v is equal to the square root of the inner product of v with itself. Right? It's just in this case the inner product happens to be the dot product, right? But that's not always the case, right? You've hopefully seen in other videos of mine on inner product spaces that the dot product, right, is not the only inner product out there on Euclidean space, or any space for that matter. And as I mentioned, the same concept, this same formula would hold true if your inner product was the dot product for lengths of vectors, norms of vectors in R3. The magnitude or norm of v is the square root of the the dot product of v with itself, or the inner product of v with itself. Again, I put a nice little bubble around this last one because it's going to be very important to us when we go to talk about norms in general inner product spaces. Okay, and then in R2, R3, for vectors we can actually visualize two-dimensional, three-dimensional space. There were some nice properties of these norms, these lengths, right, which I've got here. Right, so some properties of norms, or properties of magnitudes, lengths in R2 and R3. Right, this would hold it, and then really any Euclidean space. And really what we're going to see later is that these properties will be holding for norms on any inner product space. But for right now we're sticking to R2. Right? So suppose that, this is kind of tight here, sorry, this is I forgot about writing this before I wrote it out. Vector v and vector u, say they're vectors from R2. So you got one is a positivity. The norm of a vector will always be greater than or equal to 0. Right, the norm of a vector will always be non-negative, I guess. And with the dot product as our inner product, you would see that the norm of a vector will be equal to 0, or the only vector with a norm or a length equal to 0 in R2, R3, Rn is the 0 vector itself. Right, any other vector, any non-zero vector, is going to have a norm greater than 0. Alright, and there's this homogeneity property. This is the norm, and c is a scalar here, right? This is for any scalar c. The norm of c times v is equal to now these are actually absolute value symbols, right? The single bars will be equal to the absolute value of c times the norm of v. And again, I'll show you a picture coming up where I demonstrate this. So this just means if you take a vector in R2, R3, and multiply it by a scalar, well, that just, it gives you a vector that's pointing either in the same direction or in the opposite direction, right? But if c is negative, but on the same line, right? They're parallel vectors. So that all that happens is, the length of the vector, or the norm, gets multiplied by that factor of c, right? And to keep it positive, we say the absolute value of c. But we'll see that happen in an example coming up. And then you have the triangle inequality. Right? This is if I take the norm of u plus v, it should be less than or equal to the norm of u plus the norm of v. Alright. So, u plus v would be like, one side of a triangle is less than or equal to the sum of the lengths of the other two sides, right? That was true in, like, basic geometry class when you talk about Euclidean geometry, right? Plane geometry, actually. The length of one side of a triangle should be shorter than the sum of the other two lengths. Right? The only time you'd be getting equality here is if u and v are positive scalar multiples. They're actually vectors that are just pointing in the same direction. That's the only time you'd really get equality here, when our inner product is the dot product. And like I said, I'll show you an example of this coming up in the next several pages. All right, so let's demonstrate positivity here. All right, and again, it's just one example, but it should be for any vector. Now we're talking R2. So notice I got my coordinate plane here. This is just the plane R2. Right? Every vector basically just represents a point in R2, has two components. All right, so suppose V is the vector with components -5 and 12. Now again, you could draw that anywhere, but I've drawn it as a position vector starting from the origin, right, from 0, 0. So that means, go left 5 and move up 12. Left 5 units, up 12 units. There's the end of the vector. And, I draw it in initial point 0, 0, end point -5, 12. There's the motion. There's the vector V with components -5, 12. All right, now as I mentioned earlier, right, in R2 and in R3, pardon me, you could always set up these vectors the way they're drawn, as long as it's not a horizontal or vertical vector, as the hypotenuse of some right triangle. Right, so again, just going through the motion here, starting at 0, 0, remember I went to the left this far. Right, that's 5 units of motion. Right, I'm keeping things non-negative here. Now you could say -5 units of motion as well. But you're going to see we're going to end up squaring this value anyway, so it won't matter if it's positive or negative, right? When you square a real number, the result is non-negative anyway. And then I would travel up, right, up 12 units. So it'd be like adding these two vectors together, right, to get this vector V. And that is definitely 12 units of motion upward. Right? And you see the right triangle being formed here. Little 90-degree angle. I went straight left, then straight up. Okay. So the magnitude of V, or the norm of V, the length of V, however you want to say that. Now I could use the little formula, but again, the formula is just coming from the Pythagorean theorem. It's the square root, right? This is the length of this hypotenuse, the length of V. The square root of 5 squared plus 12 squared, which would be the same as, -5 squared, right? Like I said, -5 squared is going to be the same as 5 squared. The length of one leg squared plus 12 squared, right? And the length of the other leg squared in this right triangle. So this is the square root of 25 plus 144, which is the square root of 169, or 13 units, right? I made a nice example, so it's a nice square root. But that's not always the case. If it ended up being the square root of 150, I'd just, leave it like that. No, I'd simplify it. They'll pull 25 out of that, but still, there are going to be square roots that aren't, square roots of perfect squares like this. So just, kind of leave them or simplify them as much as you can. So the magnitude of V, the norm of V, pardon me, is 13, right, which is definitely non-negative, right? That is greater than or equal to 0. In fact, it's greater than 0. But just one demonstration of the positivity property. Right? And as I mentioned earlier, right, the only vector when we're talking this particular formula for the norm, the only vector that would have a length equal to 0 is the 0 vector itself, right? Just the vector represented by the the origin, where there's no motion, right? That would have a 0 length. But any other non-zero vector should have a positive length, a positive norm. Okay. Alright, so that was a demonstration of positivity, right? And it should work out that way for any vector in R2, R3, right? Using the dot product, using this square root of the sum of the squares of the components. Alright, so now I want to talk about that, demonstrate that homogeneity property. So there's again R2, right? Just the plane, two-dimensional vector space here. And suppose I have vector 3, negative 4, which I've drawn here as a position vector, starting from the origin. This tells me go right 3, down 4, right 3 units, down 4 units. So the magnitude of v, right, the norm of v, I can figure out right now. All right, I'll do that here off to the side. So the norm of v is just 5, right? This would be the square root of 3 squared is 9, plus, and then negative 4 squared is positive 16. And that's the square root of 25, or just, 5 units, right? So this arrow I've drawn here has a length of 5 units. If each notch, if each square, I'm assuming here that each square represents 1 unit of movement. These are all 1 by 1 squares on my grid here. Alright, so this has a length of 5 units. Now what I would like to do is multiply this vector by some scalars. So let's multiply v by, say, 2, a positive scalar. So how about let's find 2 times vector v, right? So multiplying, remember this is just, this is a vector space R2. This is under standard definitions for vector addition and scalar multiplication. So I simply multiply each component of v by the number 2. So that'd be 6, negative 8. Alright, let me draw this in. I'm going to draw this vector as a position vector. Okay. So I'll do this in a different color, right? We have the magenta here for v. So 6, negative 8. So that tells me from the origin here, if I'm starting at the origin, go right 6, down 8. So right 6 to 6 on the horizontal axis, down 8 to being in line with negative 8 on the vertical axis. Right? And so here we go. And maybe I'll pull a ruler out, make this look a little nicer. So from here, the origin to this point, notice, multiplying by a positive scalar, right, like I multiply by positive 2, gives me a vector, right, this whole thing here is 2v, gives me a vector that points in the same direction as v, right, it's on the same line. So can you see that from the picture, can you see that this is the length of twice v is just 2 times v, right? It's just v plus v, right? If I drew v, and then here's v again, right? There's v again to make 2v. So the can you see how the length or the magnitude or the norm of 2v is just twice the norm of v? Well, let's see that work out. So up here, let's do the norm of 2v using our little formula from earlier, right? The norm of this vector 2v is the square root of 6 squared, 36, plus negative 8 squared is positive 64. That's the square root of 100, which is a nice 10, which is 2 times 5, which is 2 times 5, or 2 times the norm of v, right? So the norm of 2v is simply 2 times the norm of v, right? Kind of pulling the scalar out, if you will. Now remember, in my rule earlier, it should be the absolute value of the scalar times the norm of v to keep it positive, and let me show you that here with a negative scalar. All right, so let's say I multiplied vector v here by negative 3. All right, negative 3. So let's take a look at negative 3 times vector v. Again, very simple, right? Just multiply each component of v by negative 3. So the first component, negative 9. The second component, positive 12. All right, well, let's see. Let me draw this again as a position vector starting from the origin. This negative 3v tells me go from my initial point left 9 up 12. So there's left 9 and up 12. Alright, so we'd end at this point here, it looks like. And I'll draw this also in a different color. Pull my ruler out. Let's get these in line here from the origin to that point. There we go. There's the vector. Now notice, right, there's negative 3v. Notice that vector, it's on the same line as v, right? V was this guy here, but points in the opposite direction, right? Because of, multiplying by a negative will kind of flip over your vector, if you want to think about it that way. All right, well, again, can you see how the length of this vector is just 3 times the length of v, right? If I went, here's v. If I started from here and kind of went backwards, here's v. Here's another v. Sorry, this one's straight, but that should be more straight. And then here's another v. So can you see how the length of negative 3v is just 3 times the length, right? Positive 3 times the length of v. Well, we can see that when we do the calculation, right? So the norm of negative 3v, right? The norm of negative 3v, using our formula, is the square root of the sum of the squares of the components. Negative 9 squared is positive 81, and then 12 squared, 144. And this is the square root of 225, which is a nice one again, is 15, which is 3 times the norm of v, right? That's 3 times 5, right? That's 3 times 5. 5 was the norm of v, so we have 3 times the norm of v. Notice it's not, right? It's not negative 3, it's positive 3. All right, so that's why that absolute value of c came up in the writing of the property, right? When I wrote the property for homogeneity, where the norm of cv is the absolute value of c, right? The scalar pulled out, the absolute value of it, times the norm of v for any scalar c. Okay, wonderful. So again, hopefully these were some reasonably decent demonstrations of the homogeneity property. All right, then I have now with this homogeneity property, and noticing how multiplying by a scalar affects the length. Noticing how multiplying by a scalar affects the length by that scalar. What if I asked you, and I will on the next page here, find a vector that points in that's in the same direction as v, right? So multiply by a positive scalar. But find a vector that points in the same direction as v, but has a length or a norm of one unit. That's what I'm doing on this next page. So same vector v, right? V equals 3, -4. I'm asking you to find a vector, let's say it's called u, belonging to R2, such that the norm of u is 1 and u is in the same direction of v. So that means the following, right? If u is in the same direction as v, that means that u must be equal to some scalar times v, where the scalar is a positive number. Right? That's what it means for a vector to point in the same direction. All right, and we would like, right, we want the norm of u to be equal to 1. Right. Now, this any vector with a norm of 1 is called a unit vector. I'll put that off to the side. Right. Any vector with a norm equal to 1 is called a unit vector. Okay. So what we're looking for here is a unit vector that points in the same direction of v. And this process I'm going through, finding a unit vector in the same direction of another vector. It's called normalizing that vector, which I'll write down after I'm done with this example. So remember, I'm going to write this out, right? If u points in the same direction as v, that means u can be replaced with c times v. And we want this to be, we want the norm of c times v to be equal to 1. And remember from a second ago, the homogeneity property, the norm of c times v is the absolute value of c. But c is positive, right? I know since, u is pointing in the same direction as v, so I don't need the absolute value of c here, because I already know that c is positive. So c pulled out times the norm of v equals 1. I want that to be equal to 1. Well, what's the norm of v? We already saw that. That's 5. So 5 times c equals 1. So the value of c needs to be 1/5. In fact, this will be the case whenever you're trying to find a unit vector pointing in the same direction as another vector. The scalar you need to multiply by is just 1 divided by the norm of that vector. Right? Remember, this is just 1 divided by the norm of v. This would be the scalar you'd need to multiply your vector by to get a vector with a length of 1 unit, to get a unit vector pointing in the same direction. All right, so let's so u here, this unit vector is just 1/5 times vector v. So if I multiply each component of v by 1/5, that'd be the vector 3/5 and -4/5. And there we go. Right. And you can do the little, you can do the formula. All right, let's see that this actually has a norm of 1. So what's the norm of u? Remember, it's the square root of the sum of the squares of the components. Well, 3/5 squared would be 9/25. Plus, and then -4/5 squared would be +16/25. So I'm getting the square root of, you have the two fractions with the same denominator here. Just add the numerators. 9 plus 16 is 25. That's 25/25. So that's just 1. 25/25 is 1. The square root of 1 is 1. It is one of these unit vectors. So this vector with components 3/5, -4/5 is a unit vector, right? And if I were to draw that, it would be pointing again in the same direction as v, but only be 1 unit in length. All right. So I'll just write that generalization here on the next page. Right. A unit vector u that is in the same direction as a vector v is the following. U equals, and you saw my scalar was 1 divided by the norm of v. Alright, so I should have mentioned that I should have probably mentioned that this is a non-zero vector, right? I want the norm to be non-zero, so it actually has a reciprocal, right? Times v. Right, so again, my scalar here, this is a scalar, right? This is just a number 1 divided by the norm of v times v. This will give me a unit vector that points in the same direction as v. And if you like a unit vector that points in the opposite direction, just make this negative. Remember, a negative scalar will give you a vector pointing in the opposite direction. And one other thing to point out too that you'll come across in certain texts, this process of finding a unit vector in the direction of v is called normalizing v. It's called normalizing vector v. Okay, so if you ever hear me state that in the future, I'm going to normalize this vector. That just means I'm finding a unit vector in the same direction, or I'm going to be, multiplying that vector by the reciprocal of its norm. It's really that simple. Okay, so a lot of stuff there involved with the homogeneity property, right? How to change the length of a vector by multiplying it by a scalar, and how that leads us to unit vectors. All right, then I wanted to get into a demonstration of the triangle inequality. All right. So that triangle inequality was the length, or the norm of u plus v, is less than or equal to the norm of u plus the norm of v. Alright, so I've got vectors u and v here in R2, right? R2 still. 5, 1, so again, I drew them both as position vectors starting from the origin. 5 right, 1 up for u, and then -3, 3, for vector v. 3 left, 3 up, and there's vector v. So I'll write their norms right now. So the norm of u, I won't actually write out the formula this time. Right, it would be the square root of 25 plus 1. So the square root of 26. All right, which is approximately, I'll just round this to a couple decimal places, the square root of 26, about 5.099. Right? So just a little over 5 units, right, vector u. Then vector v, right, its norm, its length, its magnitude, would be the square root of 18, right? 9 plus 9, the square root of 9 plus 9. But that is the square root of 18 is 3 times the square root of 2. Right? You can break up the square root of 18 to the square root of 9 times the square root of 2. And this is, I'll just put in the square root of 18, right, in the calculator. This is approximately 4.243 units long. Just being consistent, rounding both of these to 3 decimal places. Do whatever you want, just as long as you're consistent. Well, now let's take a look at u plus v, their sum. Right? Vector u plus vector v. Now, I'm using the standard definition of vector addition, where I just add the corresponding components, right? So u plus v, 5 plus negative 3 is positive 2, and 1 plus 3 is 4. Right? So u plus v is the vector 2, 4. Right? Now I will draw that also as a position vector. Right? So from the origin, it's telling me go to the right 2 units, up 4 units. So I would start at the origin and land at this point. All right, let's make this nice and straight. There we go. There's vector u plus v. 2 to the right, 4 up. All right, so here's this is vector u plus v. Now you might be thinking, hey, where's the triangle in all this? Right, it's called the triangle inequality. Well, if I actually drew u plus v, right? So here's vector u, and then I'll draw vector v again, but starting, instead of at the origin, I add it on to vector u. I start at the end of vector u. So vector u is, go right 5 up 1, there's the end of vector u, and then I'll draw vector v again, but add it on to vector u, and we get this, right? And you'll see if I go left 3 up 3, it takes me right to that same point at the end of u plus v. Right? So here's vector v again, right? So u plus v, and then I'm starting at the origin, ending at that point 2, 4. So I get the vector 2, 4 as the third side. Do you see the triangle now? Right? U, v, and u plus v. Make this nice little 3-sided figure. All right. So the triangle inequality, right? And again, if you remember plane geometry way back in the day, whenever you first learned that, the length of one side should be less than the sum of the lengths of the other two. Right? The only way that they're going to be equal is if u and v ran in the same direction. Right? I'll just do this off to the side. Say this is just a different u and v. Say this was u and this was v added onto it, and they ran in the same direction. Do you see how u plus v would be the exact same length? Alright, so if they run in the same direction, then the equal part will be true. The magnitude of u plus v will be equal to the magnitude of u plus the magnitude of v. But if they're not, like here, right, u and v definitely don't run in the same direction. They're not positive scalar multiples of each other. You're going to have the is less than part. All right, and let's check that. Right, what is the norm of u plus v, this third side, right? Because I've got the length of one side, right, is about 5.099. The length of the other side is about 4.243. What's the length of this third side of the triangle here? All right. So what's the norm? The norm of u plus v, and it would just be the square root of 2 squared plus 4 squared. So 4 plus 16, all right, that's 20, the square root of 20, but that can be simplified, right? The square root of 20 is the square root of 4 times the square root of 5. So that's 2 times the square root of 5, which again I'll approximate here. Right? 3 decimal places, let's say again. So I'll just put in square root of 20. Make it quick. All right, about 4.472. And you see that the triangle inequality is holding, right? The magnitude or the norm of u plus v is indeed less than the norm of u plus the norm of v. Right? And if you're less than, you're definitely less than or equal to. Right? That's even less strict, because you got 4.472 over here is less than or equal to 5.099 plus 4.243. I mean, it's very obvious, right? This is more than 9 when you add these two, right? When you add these two lengths, that's more than 9 units, whereas this is only, a little under 4.5 units. And that should hold no matter what vectors you're looking at, right? This is just, again, one example demonstrating that the norm of a sum of vectors will be less than or equal to, right, if they're pointing in the same direction, the sum of the norms of each vector individually. Right? Wonderful. Again, you can try it out with other vectors, even in R3, right? R3, try it out with some pictures in R3 if you want. Okay, now, so far, the norm I've been calculating, right, the length, the magnitude in R2, R3, has been what's called, the standard Euclidean norm, where I take the square root of the sums of the squares of the components. We're going to see that in a second here that this is not the only norm on Euclidean spaces. All right, those 3 properties, the positivity, the homogeneity, the triangle inequality. Those properties hold for different norms as well. So it's kind of like inner product. Remember how the dot product wasn't the only inner product on Euclidean spaces? Same thing with that norm we just saw. That's not the only norm. That's not the only formula that satisfies those 3 properties of positivity, homogeneity, and the triangle inequality. These do as well. So here are some other norms on Euclidean space Rn, right? So R2, R3, R4, etc. R1. Right? And these are called the P norms. Right? The P norms, P hyphen norm. So here's how they're defined. For any vector v belonging to Euclidean space, right, Rn, some vector with n components, the P norm is denoted and defined as follows. So you have the same symbol, right, the norm of vector v, but with a subscript of p. Right, so this is the P norm of v, and it's a similar setup, right? It's the pth root, not the square root. Right? Now, if p is 2, you get what we're used to. You get the standard norm that we saw, the Euclidean norm on the previous pages. But if p is 3, this is the cube root. If p is 4, this is the 4th root, etc. It's the pth root of the sum, right, the sum from 1 to n. You take the absolute value of each component, right, so that way you ensure that things are non-negative, right, that positivity holds. The absolute value of each component of the vector to the pth power. Another way to write that, the pth root of the absolute value of v1 to the pth plus the absolute value of v2 to the pth power plus the absolute value of the nth component vn to the pth power, all underneath this pth root. Right, so you see that these are similar to the square root of the sum of the squares I had earlier. Right? In fact, that is the the 2 norm, right, when p is 2, and you have square root of the sum of the squares. We'll get to that in a minute. Right, and if we let p go to infinity here, we get what's called the max norm on Euclidean space, or the infinity norm of a vector. And it's denoted in pretty much the same way, but instead of some actual value down here, you have infinity. So I have the norm of v with the infinity subscript. This is the infinity norm, or the max norm of a vector. And it's simply the max. What's the largest value of the following set, where you take the absolute value of every component of the vector, and whatever the largest of those values is the max norm or the infinity norm of that vector. All right. Probably the easiest one to calculate, in fact, if you're talking norms. And both of these norms satisfy the 3 properties there. You'll end up with a non-negative number as a result. Right? You'll have that positivity. If I multiply a vector by a scalar, you're getting the norm of that scalar multiple is just the absolute value of the scalar times the norm of the vector, right? The p norm, or the max norm. And you have the triangle inequality also holds. The p norm or max norm of a sum of 2 vectors is less than or equal to the p norm, the sum of the p norms of those vectors or max norms individually. And you can verify that on your own if you wish. I'm not going to get into that. But let's just look at a couple examples of these p norms and a max norm. All right. So here we're given a vector v equals -3, 5, -7 on R3. All right, this is a vector with 3 components, some vector from Euclidean space. Find this is the 1 norm. See the norm of v with a little subscript of 1? Right, well, the 1 norm would simply be, the first root. Well, the first root isn't a root. So there's no root symbol. Taking the first root of some expression is raising to the first power. So it's just simply this sum. It's the sum of the absolute, the sum of the absolute value of the first component to the first power, right? Where all the p's are replaced by 1 here, plus the absolute value of the second component to the first power, plus the absolute value of the third component to the first power. So our 1 norm of this vector is 3 plus 5 plus 7, and that's 15. And that's it. So the 1 norm is pretty simple to take. You're just doing the first root, so no roots, of the sum of the absolute value of every component to the first power. So the 1 norm is just the sum of the absolute values of the components. It's that simple. This is sometimes referred to as the Taxicab norm or the Manhattan norm. And if you want to take a look up Taxicab Geometry. This is a norm that is very useful when talking about distances between points in Taxicab Geometry. I'm not going to really get into that. All right, just if you'd like to look it up, please do. Okay, so that was a 1 norm of a vector. Right, notice it's totally different than the norms we were finding earlier, but it's still considered a valid norm. This 1 norm satisfies the 3 properties that every norm should: the positivity, the homogeneity, and the triangle inequality. All right, same vector. So -3, 5, -7. same vector from R3, but now I want to find the 2 norm. Well, as I mentioned earlier, if you're looking at the 2 norm, the 2 norm is the Euclidean norm, the standard Euclidean norm. Okay, so when I saw this symbol without a subscript, that's the 2 norm, right? So kind of like a square root. Remember, when you see a square root, the number p is usually not written, right? So like here, right? Like if I do the 2 norm of v, this is just the norm of v, the way it was defined earlier, right? So if no subscript is written, it's assumed to be this 2 norm when we're talking in Euclidean spaces. And let's just go through this formula here, replace all the p's with 2. So this is the square root. The square root, again, notice kind of like I said, usually in the square root, the index isn't written, the 2 isn't written. And then the now really because I'm raising to the second power, I'm going to be raising all these absolute values of the components to the second power. I don't need the absolute value, right? Because when you square a number, a real number, the result will be non-negative anyway. So I'll have, I'll just take -3. Now you could put the absolute value of -3, totally fine, but squared will make it positive anyway. Plus 5. Right, again, if you want to write the absolute value of 5, that's fine, but then it's getting squared, so it's going to be positive anyway. Plus, and the same thing, you could put the absolute value of -7 or just 7, but that's being squared, so it's going to be positive anyway. So you see this 2 norm in the p norms is exactly the same as the norm I was talking about earlier in R2 and R3. Okay, so this is the square root of 9 plus 25 would be 34, plus 49 would be 83. Right, the square root of 83 units. And there you go. Right. And this is, if you want to approximate this, might as well, since I've been doing all the other ones. It's about 9.11, approximately 9.11 units, under this norm. Earlier when I was talking the 1 norm, the norm was 15 units. Alright, maybe I will get into a little bit more here. Taxicab geometry is if I go from one point to another, when you're driving around a city, there's, you can only go left and right, up and down, especially they call it the Manhattan norm as well. Because you can only go left and right, up and down. You can't cut through buildings. Right? You can only drive on left, right, north, north, south, east, west streets. So if I thought of a unit as like a block, a city block, to get from the origin to this point, I'd have to go, 3 blocks, then 5 blocks, then 7 blocks, a total of 15 blocks. So my distance, my norm would be 15 units, right, if the units were city blocks. Whereas here, when we're talking the 2 norm, we're talking regular Euclidean geometry. So to get from the origin to this point here, traveling along this vector, I can cut it through. I can just go a straight line. I don't have to, drive around buildings. Right. Okay. So just to give you some motivation as to why they call the 1 norm the Manhattan norm or Taxicab norm. All right. So this was the usual norm. All right. And remember too, this was also the square root of the dot product of the vector with itself. So let me write that again. Remember this 2 norm was the square root of the dot product of the vector with itself. and the dot product was an inner product, right? If you thought, if that was your inner product, this was the square root of the inner product of the vector with itself. So we're going to keep this in mind. And I had this formula written up earlier. This is going to motivate our definition of a general norm on just any inner product space coming up. Okay, and then a couple more. Let's take the same vector, and say I wanted to find the 3 norm. So I'm replacing all the p's up here with 3. So I'm taking a cube root of the sum of a bunch of cubes. So this time absolute value would be needed, because when you raise to the 3rd power, you're not always positive, right? So this would be the cube root for this same vector, right? P is 3 this time, of the absolute value of -3, so just 3 to the 3rd power, plus the absolute value of 5, so just 5 to the 3rd power, plus, and then again the absolute, because I'm raising to odd powers, absolute value is necessary here to keep things positive. The absolute value of -7 is 7 to the 3rd power. Alright, so I'll just punch this in. Alright, we got, so 3 cubed is 27, right? 3 cubed plus 5 cubed is 125. Plus 7 cubed is 343. So we're getting, this is the, I'll say equal first, equals the cube root of 495 is approximately, somebody just take this number here, raise it to the 1/3 power, right? Remember, raise into the 1/3 power is the same as the cube root, right? Just like the half power was square root. So that's about 7.91 units, right? So there's the 3 norm of this vector, right? And again, the 3 norm, the way I have it, the cube root of the sums of cubes, right, of the absolute values of the components, satisfies positivity, homogeneity, triangle inequality, and you can check that if you want. Alright, and then finally the max, you could do this with 4 norm, 5 norm, 6 norm, just replace p with 4, 5, 6, 7. Now this max norm, right, so again, same vector, right, same vector. Let's find the max norm. Now remember, the max norm is what's the largest value, the maximum value of the absolute value of the first component, the absolute value of the second component, the absolute value of the third component. And it's that simple. Pardon me, it's that simple. What's the largest of 3, 5, and 7? 7. 7. Alright, and this is kind of really like a limiting value, if you think about it. You notice how I started off with, the 1 norm was 15, the 2 norm was 9.11, a little smaller, the 3 norm was 7.91. What you'd notice is that if you did the 4 norm, the 5 norm, the 6 norm, 7 norm, 8 norm, their limiting value would be 7. You see how they were kind of decreasing here to 7? And go ahead and try that out. Find the 4 norm, the 5 norm, the 6 norm, the 7 norm. And you'd see that it'd be getting closer and closer and closer to 7. Right? The max norm, the infinity norm. Right? Really, it's just what happens as p approaches infinity in this formula. Right? The limit. Okay. So there was a bunch of examples there of some other norms for vectors in Euclidean space, right? R1, R2, Rn. The one we're going to use most often, of course, though, is the 2 norm, right? The one with the squares. This is used most often because in R2 and R3 it has the most real-world application. It's actually the real distance between vectors and between points in two-dimensional and three-dimensional space. So we're going to use the 2 norm much more often than any of the other norms, p norms that I've mentioned. All right. So finally, we've talked about Euclidean spaces for a lot here, right? It's been an hour. Now let's get into just general inner product spaces, right? My whole first part of the video, except for the p norms, right? Before the p norms, I was doing the norm of a vector on R2 or R3 with the dot product as the inner product. But that is not always the case, right? The dot product is not always an inner product on some vector space. All right, so what we're going to do now is get into norms on general inner product spaces. Right. So we'll recall here, again, just going back to what I showed you this earlier, coming back to it, recall that on Euclidean space Rn, with the Euclidean inner product or the dot product, right? The inner product of u and v is the dot product of u and v. The norm of a vector was the square root of the dot product of that vector with itself, or the inner product of that vector with itself. This will be generalized to any inner product space. All right, this formula here is how the norm of a vector will be defined in any inner product space. So the norm on any inner product space V with inner product, the little wedge form here, inner product of u and v, not necessarily the dot product, right? It could be something else now, is the function such that for all v and v, all the vectors in this inner product space, the norm of v is the square root of the inner product of v with itself. Or you could say the norm of v squared is the inner product of the vector with itself, right? If you just square both sides. So this is how the norm of a vector will be defined for any inner product space. And of course, just like with my Euclidean spaces earlier in the dot product, a unit vector is a vector u, that has a norm of 1, right, where this ends up being the number 1. That will be called a unit vector. And the finding of a unit vector in the same direction as vector v will entail the same procedure, that normalizing procedure I did earlier, where I just multiply v by the reciprocal of its norm, and that resulting vector will be a unit vector in the same direction as v. Okay. And it has all the same properties, right? This is the same as we saw before, just it wasn't just any inner product, it was a dot product, but this definition of a norm here for any inner product space has the same properties. Right? So here they are again. Properties of any norm, right? Any norm for any vectors u and v from inner product space v and any scalar c. You have those same 3 properties holding: the positivity property, that homogeneity property, and the triangle inequality. They look exactly the same, right? The norm of any vector will be greater than or equal to 0. The norm of a scalar multiple of a vector will just be the absolute value of that scalar times the norm of the vector. And the norm of the sum of 2 vectors will always be less than or equal to the norm of one vector plus the norm of the other. Right? The same properties that held earlier when my inner product was the dot product. But now we're going to see other inner products and use these same definitions. Use this definition here, Right, this is how we're defining norm, again, on any inner product space. The square root of the inner product of the vector with itself. And what I'm going to do now is just demonstrate just one example of each of these properties again, but on some other inner product spaces. Alright, so my first example is to demonstrate positivity. Okay. So I know it's a Euclidean space, I get that. Let V equal, let's say the vector 2, negative 3 on R2. But this time, instead of the inner product being the dot product, I have the inner product is one of those weighted Euclidean inner products, right? Where it's like the dot product, but the coefficients aren't 1. Right? There are other positive numbers. So here the inner product of two vectors is 3 times the product of the first components plus 4 times the product of the second components. And let's find the norm of V under this inner product. So you got to really pay attention, okay? Because I know you're probably going to want to see this and be like, hey, it's just the square root of 4 plus 9. It's just the square root of 13. That is not the case this time. It's the square root of 13 when our inner product on the space is the dot product. This is not the dot product. So we cannot use that same formula for the norm of V. We must use this formula. This is how the norm of a vector is defined on any inner product space. It's the square root of the inner product of the vector with itself. Right, we must use this. Right, again, must use this. And even when the inner product was the dot product, you saw that this formula was holding. Right. Okay. And notice now there's no subscript here. It's not the 2 norm or 3 norm, right? Those were defined differently. Right? When there's no subscript, you're using this formula. Alright, so what is the inner product of V with V? Well, based on the inner product given, it's 3 times, the product of the first component, so 3 times 2 times 2. Right, because they both have the same first component. They're both V. Plus 4 times the product of the second components, which is negative 3 and negative 3, so negative 3 squared. So we have 3 times 2 squared, 3 times 4, that's 12, plus 4 times 9, so plus 36. This is 48. So the norm of this vector under this inner product, the norm of this vector under this inner product, you have to really pay attention, is the square root of 48. Or, you can break this up to the square root of 16 times the square root of 3. That's 4 times the square root of 3. And again, you can approximate that. This time I won't. Punch that into calculator or whatever. Should be, close to 7, right? It's close to 7 units. And again, this is not the square root of 13. Like you're like, hey, I thought it was the square root of 13. That's under the dot product. The way the norm is defined depends on how the inner product is defined. So please pay attention to how the inner product is defined before you go finding your norm. Okay. So, and you can see that's greater than or equal to 0, right? And it should be. Right? If you have a proper inner product, right? Remember, if you have a function that satisfies all 4 of those inner product axioms, symmetric, homogeneous, additive, and positive definite. If you have a proper inner product defined, then the norm, the way it's defined here, should be a non-negative value, right? Should be greater than or equal to 0. And if it's truly a proper inner product, right, this will only be 0 when v is the 0 vector, right, from that positive definite property for inner products, right? The inner product of a vector with itself will be positive or 0, but only 0 when the vector is a 0 vector. But we're definitely seeing here this is greater than or equal to 0, and it always should be on any inner product. All right. Homogeneity. This time I'm working in a vector space, an inner product space that's not R2 or R3, not Euclidean. So here, my vector space is P2. Remember, this is the set of all polynomials of degree 2 or less. They all look like this, P of x, Q of x here, where there's a constant plus a linear term plus a quadratic term. So suppose I have a vector f, which equals 1 minus x plus 3x squared. Right? This is a vector, a polynomial from P2. With this inner product, now you might say, this looks almost exactly like the dot product in R3, but it's on vectors in P2, it's on these polynomials, where the inner product of polynomial P with polynomial Q is the product of their constant coefficients plus the product of their linear coefficients a1, b1 plus the product of their quadratic coefficients a2, b2. And you can double check, this is a properly defined inner product. It satisfies all 4 inner product axioms. Let's find the norm of f under this inner product. What's the norm of my polynomial f of x up there? Again, this should be the square root of the inner product of f with itself. Always using this. This is how the norm is defined for any inner product space. All right, so let's find this. What is the inner product of f with itself? So this would be, a0 is 1, a1, is -1, the coefficient of x to the first, and a2 is 3. Right? So a0, b0, they're both 1, so 1 squared plus a1, b1, that's -1 times -1, so -1 squared, plus, and then a2, b2 is 3, 3. They're both the same for the coefficient for the x squared, 3 squared. So this is 1 plus 1 is 2, plus 9 is 11. Right. So there's the inner product of this polynomial. This inner product of this polynomial with itself is 11, a non-negative number. So the norm of this polynomial is the square root of 11. Now notice I'm not saying length anymore now. I'm not going to say length or magnitude. I'm going to stick with norm. Because what does it mean to, what is the length of a polynomial? What is the length of a matrix, of a function? That doesn't make any sense really. The only time length really makes any sense is when you're in R2 or R3 and you can visualize a picture of a length. So I'm going to say norm from here on out, when we're talking other vector spaces, other inner product spaces. And the norm of a polynomial is just the square root of the inner product of that polynomial with itself. Okay, so we have the norm of f is the square root of 11. Now let me demonstrate that homogeneity property. I'm going to multiply this polynomial f by some scalar. All right, so let's look at, how about 2 times f? Now again, it can be any real number you wish. Right? I'm using nice ones like 2 and 3. You can multiply by pi, square root of 3, whatever you want. 2 times f of x, what does that look like? So, I mean, it's just the way you would normally multiply a polynomial by 2, just distribute the 2. Right, that'd be 2 minus 2x plus 6x squared. And let's see what the norm of this vector would be. Well, remember the norm of 2f, right? The norm of 2 times f is defined to be the square root of the inner product of 2f with itself, of 2f with 2f. So let me find that inner product. Now you could use the homogeneity property of inner products to say that this is just going to be 4 times the inner product of f with f. Pull the 2 out of the first slot and the 2 out of the second slot because it's homogeneous in the first slot and the second slot. But let's go through. All right, let's go through it and actually do it. All right, so what is the inner product of 2f with 2f? So that's going to be 2 squared plus negative 2 squared plus, based on the way the inner product is defined, plus 6 squared. So that's 4 plus 4, which is 8, plus 36 is 44. And do you see how that's just 4 times 11? See how this is just 4 times the inner product of f with f, as I said it would be, right? You pull the 2 out of the first slot, 2 out of the second slot, using the homogeneity property of inner product. So our norm of 2f is just the square root of 44, which, when you break it up to the square root of 4 times the square root of 11, that's 2 times the square root of 11, and oh look, that's just 2 times the norm of f. Right? The norm of f was the square root of 11. And so you see the homogeneity property holding. Right? The norm of 2f is just 2 times the norm of f. Right? And so the norm of negative 2f would also be 2 times the norm of f. Remember, it's the absolute value of the scalar. We want to keep things positive, keep things non-negative. Right? The norm of negative 3f would just be 3 times the square root of 11. Right? Again, if you multiply this by negative 3, you get negative 3 plus 3x minus 9x squared, and found the norm of that, it would just be 3 times the square root of 11, right? Again, the absolute value of negative 3, positive 3 times the norm of f times the square root of 11, and so on, right? You could find all sorts of other norms, right, of scalar multiples of f, right? So now, what if I asked you to normalize f under this inner product? Find a unit vector in the direction of f. What if I asked for that? Now, I already had the norm of f, right? The norm of f was the square root of 11. And don't forget what this is called again, right? I said it out loud. When I say find a unit vector in the, again, I put direction in quotes here because, how do you really say what direction a polynomial is pointing in, or what direction a matrix is pointing in, or a function? So the concept of direction is a little loose here. But when I say, it still has the same concept as, if two vectors are in the same direction, that just means they're positive scalar multiples of one another. That's all that means by in the direction of. So when I say here, find a unit vector in the direction of this polynomial, right, this same polynomial I had up here, the 1 minus x plus 3x squared from the vector space P2 under this inner product, right? It's still under this inner product. Again, this was called normalizing, right? So I'm basically asking myself here to normalize f, right? Find a unit vector in the direction of f. Well, remember, I'll call this u, say u of x. Remember, I wrote this up earlier. You just take, to normalize f, you just take that vector. To normalize a vector, you take that vector and multiply it by a scalar, a positive scalar. And that scalar is simply the reciprocal of the norm of that vector. So I take f of x and I multiply by the reciprocal of the norm of f of x. This will be the normalization of f. A unit vector or a unit polynomial, under this inner product that is in the same direction as f, right? Meaning a positive scalar multiple of f. So the polynomial I'm looking for, I'll call it u of x for a unit vector, is 1 over the square root of 11 times f. And if I multiply that out, right, well, that's just 1 over the square root of 11 for the constant minus 1 over the square root of 11 times x plus 3 over the square root of 11 times x squared. There you go. And if you would like to rationalize the denominators, be my guest. This would be the square root of 11 over 11. This would be the square root of 11 over 11. And this would be 3 times the square root of 11 over 11. Totally fine. And you can double check. Find the norm of u. Right, let's find the norm of u. The norm of this vector, u of x, should be equal to, again, the square root of the inner product of u with u. So it's the square root of, and again, using this inner product, that's 1 over the square root of 11 squared, so 1/11th, plus negative 1 over the square root of 11 squared, that's 1/11th again, plus, and then 3 over the square root of 11 squared, it's 9/11ths, and we get the square root of 11/11ths, which is just 1. It is indeed a unit vector. It has a norm of 1. Great. Again, very easy to normalize a vector. Just multiply that vector by the reciprocal of its norm, and you'll get a unit vector that is in the same direction, where by same direction I mean a positive scalar multiple of it. Great. All right, then one demonstration of the triangle inequality. And then on the last page, I want to talk about that Cauchy-Schwarz inequality one more time. Which, I haven't talked about in this video, but in a previous video I did bring up the Cauchy-Schwarz inequality on an inner product space. Alright, so here's one. Alright, the triangle inequality. So this time my vector space is that C with the interval from 0 to 1, the closed interval from 0 to 1. Remember, this is the set of all continuous functions on the closed interval 0 to 1 in the real number line. So I just got a couple polynomials here, right? So I guess you could also say these are from P2, but let's just say you could use I could use sine x, cosine x, e to the x, right? Other functions besides polynomials as well in this. So say f of x is negative x, g of x is x squared minus x plus 2. And again, both of these are functions that are continuous on the interval from 0 to 1. And we have that integral inner product, with the inner product of f and g being the integral of two vectors, being the integral from 0 to 1 of the product of those two vectors with respect to x. Right? And if you've seen other videos of mine on inner products, you've probably come across this integral inner product, which is similar to the dot product over an infinite number of arguments. All right, well, let me find. Remember, if I'm gonna try to demonstrate the triangle inequality here. So I've got these two vectors separately, and then let's take a look at their sum. All right, what's f of x plus g of x? Well, again, I just picked a couple polynomials here, so just combine some like terms. that would be x squared minus 2x, right? Because you got the negative x, and then plus 2. And I'm trying to demonstrate that the triangle inequality should hold for norms on any inner product space, right? The way we define the norm as the square root of an inner product of a vector of itself. All right, so let me find this. What's the norm of f plus g? So that will require finding the inner product of f plus g with itself. All right. So that's the integral, right, the way the inner product is defined here. The integral from 0 to 1 of, f plus g, both functions are f plus g. So this f plus g squared, so x squared minus 2x plus 2 squared, right, with respect to x here. Okay, so I'm going to have to multiply this out. Alright, so when I multiply this by itself, I get, if I distribute the x squared, I have an x to the 4th minus 2x cubed plus 2x squared. Then I would distribute the negative 2x to it again, and it would be minus 2x cubed plus 4x squared, and then minus 4x, right, and then distributing the 2 to itself, plus 2x squared minus 4x plus 4. Right. And then we combine like terms. So this is the integral from 0 to 1 of the following polynomial, right, x to the 4th minus 4x cubed plus 8x squared minus 8x, then plus 4. Alright, let me do some simple antiderivatives here. I'm going to change markers. This is getting kind of faint. So now I'm just going to go and say, when I do the antiderivative of all these, they'll all have an x in it, at least x to the 1st. So when I plug in 0, that won't matter. Right, I'd just be plugging in 1. Alright, so I'd have a 5th minus 1, right, because this would be just x to the 4th, plus 8/3. Then 4 plus minus 4 plus 4. Right, and that's all. That's what I would get. Now the minus 4 plus 4 is gone. You can get some 15ths in here. Right, this would be 3/15 minus 15/15 plus 40/15. So we're getting 25 there, plus 3, 28/15. And it should be non-negative. Remember, an inner product of a vector with itself should be non-negative, right? Greater than or equal to 0, which this is. Okay, so this is the inner product of f plus g with itself, 28/15. So the norm of f plus g, or f of x plus g of x, is the square root of this. Remember, it's the square root of the inner product of the vector with itself. So the square root of 28/15, which I will approximate. So the square root of, and then make sure it's all inside the square root, 28/15. So approximately 1.366 is the norm of f plus g. Alright, then let's take a look at the norms of these separately. Alright. So on the next page, now the norm of f is pretty simple. And under this dot product, under this inner product, not the dot product. So to find the norm of f, right, first I want to find that what's the inner product of f with f, right, f with itself. That'd be the integral from 0 to 1 of f of x times f of x, right? So negative x times negative x are just x squared And I hope you see that this is 1/3, alright? That's just 1/3. Okay, so the norm of f under this inner product is the square root of 1/3, which I will approximate again. Square root, square root of 1/3, about 0.577. Alright, and then for the norm of g, I would first find the inner product of g with g. So this is the integral from 0 to 1 of just, g squared, so x squared minus x plus 2 squared. And again, I'm going to do this off to the side here. When I distribute the x squared, it'll give me x to the 4th minus x cubed plus 2x squared. And then I'll distribute the negative x to it, minus x cubed plus x squared minus 2x, and then distributing the 2 gives me plus 2x squared minus 2x plus 4. Alright, then we'll combine like terms. So this is the integral from 0 to 1 of x to the 4th minus 2x cubed plus 5x squared minus 4x plus 4, right, with respect to x. And again, when I do the antiderivative of this, they'll all have at least an x in it, so I don't, plugging in 0 won't mean anything, won't contribute. So it'll just be the value at 1. So again, this is 1/5 minus a half, right, from that term, and then it'll be 5 plus 5/3. Then minus 2 plus 4. Right. Then we combine some stuff. This will be plus 2 here. These two. And get everything to be 30ths, right? The least common denominator. So this would be 6 30ths minus 15 30ths plus 50 30ths plus 60 30ths. Right, the 2 at the end there. So this is 110, and then minus 9, right, 6 minus 15, 110 minus 9, this is 101 30ths. Right. And yeah, so that's the inner product of g with itself, and therefore the norm of g will be the square root of that, right? The square root of the inner product of g with itself. So the square root of 101 30ths. All right, we get that approximation again. So the square root of 101 30ths. So about 1.835. I go to 3 decimal places again. All right, let's see. Now, is the norm of f plus g less than or equal to the norm of f plus the norm of g? So the norm of f plus g, that was, I found that on the earlier page, about 1.366. Right, this was approximately 1.366. Is that less than or equal to the norm of f plus the norm of g? Well, remember these were approximately, I just got these, so 0.577 for the norm of f was about, plus, and then 1.835, I mean definitely, right, it's even less than the norm of g, 1.835. This is true, and it should be, right? It should be for any pair of vectors in an inner product space. The triangle inequality should hold for your norm, right, where the norm again is the square root of an inner product of a vector with itself. Wonderful. All right, so be aware of that definition of norm. Right? Now, I'm not going to do any examples with this, but the final page I have here is just to refresh your memory as to the, I did a video recently on, the Cauchy-Schwarz inequality over an inner product space, and went through a few examples where I just verified that it was true for, certain given vectors over a given inner product space. So remember, the Cauchy-Schwarz inequality stated the following. For any vectors u and v from an inner product space V, remember the inner product of u and v squared will always be less than or equal to the inner product of u with itself times the inner product of v with itself. Now in that video I said, okay, well, if you take the square root of both sides, you get the absolute value of the inner product of u with v is less than or equal to the square root of the product of, the inner product of u with u and the inner product of v with v. Well, these are real numbers, and these should be non-negative, right? The inner product of a vector with itself should be non-negative. So you can break this up to the square root of the inner product of u with u times the square root of the inner product of v with v. Well, remember what those are defined now as. The square root of the inner product of u with u is the norm of u, times the square root of the inner product of v with v, that's the norm of v. So an equivalent way of stating the Cauchy-Schwarz inequality is that the for any pair of vectors on an inner product space, the absolute value of the inner product of those two vectors will be less than or equal to the norm of one vector multiplied by the norm of the other. And again, you can go back to my video on the Cauchy-Schwarz inequality and take a look at the examples. I just verified that this was true, right? The one with the square, where both basically just square both sides. I verified that this statement was true. But if this statement is true, then this statement involving the norms would also be true. Right? That the absolute value of an inner product of two vectors is less than or equal to the product of their norms. And if you'd like to, go back and you could go back here to this example when I was showing you the triangle inequality. Now, I didn't do the inner product of f with g. We could take f times g and integrate. You'll see that the absolute value of that number will be less than or equal to the norm of f times the norm of g, right, which was about 0.577 and about 1.836 or 1.835. You can verify that for yourself if you wish, but this is big, right? This is a nice big result involving norms, right? Same statement as I had earlier, like I said, but now involving this norm symbol. Okay, so again, a lot of stuff there, a lot of stuff to take in, but I think the biggest thing to take away, right, the biggest things to take away from this video are this formula, that the norm of a vector on any inner product space is defined as the square root of the inner product of that vector with itself. Right. There may be some other norms, right, but they'll have some, if you're talking about a p norm on Euclidean space, you'll see a subscript, the 3 norm, you saw the 3 norm, the 4 norm. You're not going to see that too often. Right? Please add this in your mind, that the norm of a vector is the square root of the inner product of that vector with itself, and you have to be careful. You have to know how the inner product is defined. It is not always the dot product. And also the properties, right? These are properties that will hold for any norm on an inner product space: the positivity, the homogeneity, the triangle inequality, as I showed you with some examples of those. Alright, so I hope this video is informative, and that you have fun and enjoy practicing problems involving norms, finding norms, and verifying properties. And thank you very much for watching.